In this lesson, we will discover and understand, learn about the properties of logarithms. Here are 4 different properties that we will discuss briefly in this lesson. There'll be some more properties later on, but for now, these are the first 4 I want to discuss with you. The first says that log base b of 1 will always be equal to 0. So you can interpret this first property as follows. If the argument is 1, then the answer, the logarithm, is equal to, the exponent is equal to 0. Whenever the argument is 1, then the exponent, remember a logarithm is an exponent, so this represents the exponent over here, is always going to be 0. You can confirm this by rewriting this, if you'd like, in exponential form. In other words, rewrite this log equation as an exponential equation. And we did something like this in an earlier lesson. It would be b to the power of 0 is equal to 1. And you and I know that this is always true. Any non-zero number raised to the power of 0 is equal to 1. Because this statement is always true, it's actually the 0 exponent rule, then this statement is always true. So if the argument of your logarithm is 1, then the exponent must be 0. The next rule says that log base b of b is equal to 1. So if the base and the argument match, if these are the same value, then it's just equal to 1. The logarithm is equal to 1. The exponent is equal to 1. Now you can, to help you understand that this is true, rewrite this in exponential form. It'll be b to the power of 1 will just give you b, correct? And we know that's true. Any number raised to the power of 1 is that same value, that same number. So because this is always true, this statement is also true. If the base and the argument are the same, the answer, the logarithm, is just 1. The next property says that log base b of b to the power x is just going to give you x. To understand what this is saying, consider maybe rewriting this as an exponential equation. It'll be b, base b to the power of x will give you the argument b to the power of x. And you and I would look at this statement and be like, well, of course, b to the power x is equal to itself, right? B to the power x is equal to b to the power x, of course. So that means this statement will always be true. Finally, we have this last property, that is b to this power, p to the power of, did I say p? I meant b. b to the power of log base b of x is equal to x, as long as x is a positive value. Now, this restriction has to be here because x has to be your argument, happens to be the argument, and the argument by definition of a logarithm has to be positive value. Now, to understand why this is true, consider rewriting this as a log equation. Right now it's written as an exponential equation with base b and this power is equal to x. So I'm going to rewrite this using a logarithm. So here we go, log. Now the base of my logarithm will be b. So log base b. Now a logarithm is an exponent, so what I'm going to write here, I'm going to set this logarithm equal to the exponent, and the exponent happens to be log base b of x. Which leaves me with the argument must be x, right everybody? So what you get here, if you rewrite this exponential equation as a logarithmic equation, you get log base b of x is equal to log base b of x. And again, when you hear that and read that, you're probably saying, well, of course it is. The left-hand side is exactly what the right-hand side is. So because this statement is true, this statement is also true. B raised to the power of log base b of x is just going to give you x. Now let's use these properties in the following example. They're going to ask us to simplify some log expressions. The first one here is log base pi of pi. Now don't let pi throw you off. It's just a number, right? So log base pi of pi. Now please remember that a logarithm is, you're probably tired of hearing me say this, a logarithm is an exponent. So they're asking you here, to what exponent do you have to raise pi, that's your base, in order to get your argument, which is pi, right? To what exponent do I raise pi in order to get pi? And so I hope you look at this and think, oh, 1. If I raise pi to the power of 1, I'll just get pi. So then my answer is 1. This is equal to, log base pi of pi is equal to 1. If you reference the properties that we were just talking about, this would be property number 2, where the base and the argument match. And you always get 1. The next log expression I want us to consider is log base 7 of 7 to the power of 9. Now again, a logarithm is an exponent. So really they're asking you for the exponent to which you would have to raise base 7 in order to get the argument of 7 to the power of 9. What power do I raise 7 to in order to get 7 to the power of 9? I hope you're looking at this and thinking, oh, you would have to raise 7 to the power of 9 if you expect to get 7 to the power of 9. So then your answer is just 9. Log base 7 of 7 to the 9th power is just 9. If you look back at your properties, this is property number 3. This next one is interesting. It's base 6 raised to the power of log base 6 of 5. If you look at your property, this would be property number 4. Basically, this is up here. I want you to understand that this power is a logarithm. And don't forget that a logarithm is an exponent. So this notation up here is describing the exponent to which you would raise 6 in order to get 5. So up here is basically the exponent to which you raise 6 to get 5. So here we are raising 6 to that exponent, so we should expect to get 5. This is just equal to 5. Okay? And again, please reference property number 4 for this one. The last one like this, log base 3 of 1. So again, a logarithm is an exponent. So they're asking you, to what exponent would you have to raise 3 in order to get 1? I hope you're looking at this and thinking 0. If you raise 3 to the 0th power, you will get 1. So the exponent that they're looking for is indeed 0. That's your answer. All right, good job, everybody. Now the rest of this lesson will focus on 3 rules: product rule, the quotient rule, and the power rule. The product rule says that if you have a sum of logarithms with the same base, then you can rewrite the sum of 2 logarithms as a single log, and what you would do is multiply the 2 arguments together, this argument times this one. So a sum of logs can be rewritten as a product of, the sum of 2 logs can be rewritten as a single logarithm, okay? And notice that the arguments is now a product, right? It's m times n. The quotient rule says that if you have a difference of logarithms, obviously with the same base, then you can rewrite that as a single logarithm, and notice that you are dividing the arguments. It's the first argument, m, over or divided by the second argument, n. Finally, log base b of m to the power of p. M to the power of p is an exponential expression. So the power rule is saying that if you're taking a logarithm of an exponential expression, that's the same thing as this power coming down to the front as a coefficient. So it's now p times log base b of m. You can rewrite this left-hand side as the right. So what I'm going to do is I'm going to take you through some examples here to practice using all of these rules, okay? Let's start with practicing the product rule. All right, we want to write this expression as the sum of logarithms, and then simplify if you can. All right, this is using the product rule. The product rule says that if you have a product, you can rewrite it as a sum of logarithms, right? So what I can do is rewrite this as log base 5 of the first factor plus log base 5 of the second factor. You see, this is a sum of logarithms, and that always can come from a single log, right? And so what we do is we split it into two logarithms with the same base, right? Base 5, base 5. And then this is the first factor, and then this argument is the second factor. Now, simplify if you can. This first one here is log base 5 of 5. To what power do you raise 5 in order to get 5? Well, that's 1. So then this is 1 plus log base 5 of 3. That's your final answer. Okay, everybody? We have the log of 10,000x. Log of 10,000x. Let's not forget that whenever the base is not written, it's assumed to be 10. So this is a common log. Log base 10 of 10,000x. Now, I'm going to use the product rule here to rewrite this as log of 10,000, that's the first factor, plus log of just x. Now remember, your base is 10 here, so that basically this logarithm is asking you for the exponent to which you raise 10 to get 10,000. And that's just the number 4. If you raise 10 to the power of 4, you will get 10,000. So the final answer is just 4 plus log x. Let's look at another one. We have log base 9 of 81mn. All right, we're going to use the product rule. And because there's 3 factors, one of them is 81, m, and then n, then I'm going to have a sum of 3 logs, okay? So the first one will be log base 9 of 81 plus log base 9 of m plus log base 9 of n. This is the product rule. Now, this first logarithm is the only one that can simplify. I would have to raise 9 to the power of 2 in order to get 81. So this first logarithm is just equal to 2. So your final answer is 2 plus log base 9 of m plus log base 9 of n. Okay, I hope you're getting this. I hope you feel pretty good about that set of examples. Let's continue. All right, this time around, we're going to want to use the quotient rule to rewrite this expression as a difference of logarithms, and then we'll simplify if we can. Now, because this is written as a quotient, 5 divided by 2, that's why I'm using the quotient rule. Now, the quotient rule says that this can be rewritten as the natural log of the numerator minus the natural log of the denominator. Now, both the natural log of 5 and the natural log of 2 cannot be simplified. Okay, so we just leave it like that. The next one is log of 100 divided by x. Again, because you see division, this is the quotient rule. So it'll be log of 100 and then minus log of x. Now you can simplify further here. Remember, this is a common logarithm, meaning the base is 10. You would have to raise 10 to the power of 2 in order to get 100. So then this is just 2 minus log x. Final answer. All right, cool, let's move on. All right, we're going to write the following expression as the sum and or the difference of logarithms of a single quantity. And then we'll simplify if we can. This is not one quantity. This is not a single quantity. It's x times y, then divided by 100 times z. There's a lot going on here. Now, this is a common log. So what I'm going to do here is I'm going to rewrite this. Now, the first thing I'm going to do is use the quotient rule to undo this division here. The quotient rule will say that this is equal to log of the numerator minus log of the denominator. Now, for this logarithm, because it's x times y, I'm going to use the product rule. And I'll use the product rule here as well. 100 times z is what's telling me that I'm going to use the product rule. But I have to be careful. Here we go. Log of x times y can be rewritten using the product rule as log of x plus log of y. Now you got to be careful with this next part. It's going to be minus and then open a set of parentheses because this one logarithm will turn into a sum of logs. So you're going to have log of 100 plus log of z. That was us using the product rule. All right, so then you're going to have log of x plus log of y minus. Now what I'm going to do is distribute this minus to both of these terms, but in addition to that, we already talked about how log of 100 is just the number 2. So I'm going to rewrite it as minus 2 and then minus log of z. Now, you're done here because notice that the argument for each of our logarithms is a single quantity. This is just x, just y, just z. Okay, we're now going to use the power rule, and we're going to use the power rule to write this logarithm without an exponent. This is the exponent, 4. Now, the power rule says that whenever you are taking the logarithm of an exponential expression, like 7 to the power of 4, the power can come down to the front, right? So in other words, you can rewrite this as 4 times log base 3 of 7. That's it. So then this is equivalent to the original expression. The 4, basically, the exponent of 4 just comes down. The power comes down like that. That's whenever you're taking a logarithm of an exponential expression. The next one is log of the 4th root of 5. Now, keep in mind that this basically means log of 5 raised to the power of 1/4. That's what the 4th root means. Now, according to the power rule, this power right here comes down to the front, so then it's 1/4 times log of 5. Final answer. I rewrote the expression without an exponent. The last one like this says log of x to the 9th power. Now again, because you're taking a logarithm of an exponential expression like x to the power of 9, then that means this power can come down to the front like that. So then rewriting this would just be 9 times log of x, and that's your final answer. So we just practice how to write or rewrite an expression without an exponent. All right, we're going to wrap it up with the next few examples. Here the instructions say write each expression as the sum and or difference of logarithms of a single quantity. All right, everybody, we're going to have to use all 3 of our rules for this example. Now follow this carefully, okay? The first thing I'm going to do to unravel all of this is I'm going to undo this division by using the quotient rule. All right, so then this is going to be equal to the natural log of the numerator, like that, minus the natural log of the denominator. That's the quotient rule. Let's keep going. Now I am going to use the product rule to rewrite this first logarithm as the sum of 2 logs, because this is 5 times the cube root of x. So then this is going to just be equal to the natural log of 5, that's the first factor, plus the natural log of the cube root of x, that's the second factor. I'm talking about up here. 5 is the first factor, cube root of x is the second factor. And then, so that was me rewriting this single logarithm as a sum of these 2 logs. In this same step, I'm going to use the power rule to bring this 2 down to the front, okay? So then you're going to see me write minus 2 times the natural log of y. The last thing I'm going to do to wrap this up, This is the natural log of 5, so this one's good. It's a logarithm of a single quantity, and so is the backside, the natural log of y. That's a single quantity. But the cube root of x is not a single quantity, so I'm going to bring this power down. Don't forget that the cube root is the same as 1/3 as a rational exponent. So I'll bring down the power of 1/3. So the final answer will be the natural log of 5 plus 1/3 times the natural log of x minus 2 times the natural log of y. So now this expression is a sum or difference of logarithms, all of a single quantity. Let's try that again, this time with log base 2 of the cube root of x squared y over z. Now, the first thing I'm going to do here is use the power rule. The power rule to undo this cube root. Now, don't forget that the cube root of something is the rational exponent of 1/3. So then the power rule will say this is equivalent to 1/3, right? That's the power coming down, times log base 2 of x squared y over z. Okay, that was us using the power rule. Now, let's undo this division right here using the quotient rule. Okay, now keep 1/3 out in front of everything. Okay, I'm actually just going to open up a set of parentheses. So you're going to have log base 2 of the numerator minus log base 2 of the denominator. Okay, this last term is fine. It's log base 2 of a single quantity, z. This one here, this log has to be rewritten using the product rule because it's x squared times y. So I'm going to break this logarithm up into a sum of logs. So it would be 1/3 times log base 2 of x squared plus log base 2 of y, and then minus log base 2 of z. I want to make sure that this is a 2 and that's a z. I want to make sure that you understand this to be a 2 and that to be a z. Okay, guys, this term is done here. This term is done. It's just this one. This 2 as an exponent has to come down, or it can come down. So then this is just 1/3 times 2 times log base 2 of x plus log base 2 of y minus log base 2 of z. Now, we're practically done. The only thing I'm going to do last here is to distribute the 1/3. So I'm going to have 2/3, right? Because 1/3 times 2 is just 2/3 of log base 2 of x plus 1/3 times log base 2 of y minus 1/3 times log base 2 of z. This is the final answer because it's all a sum or difference of logarithms of a single quantity. Okay, we'll wrap it up with this example. The instructions say write this expression as one single logarithm. Write this as a single logarithm. Okay, the first thing we're going to do, we have to start compiling all of this together so that it all comes together as one single logarithm. The first thing I'm going to do is I'm going to take all of my coefficients. So I'm going to take 2/3, I'm going to take 5, or you can take -5 if you'd like, but I'm just going to take 5 and leave the negative there. And I'm going to take these coefficients and I'm going to put them back up as powers on the arguments. Okay, this is using the power rule. So then you would have log base b of x to the power of 2/3 minus log base b of y to the 5th plus log base b of x plus 4, that's a little sloppy, hold on, log base b of x plus 4, all of that cubed. All right, cool. Now what I'm going to do is I'm going to work left to right. So I'm going to combine these two logarithms to be a single log. How? Well, using the quotient rule. How do you know it's the quotient rule? Well, because this is a difference. And the quotient rule says you can write the difference of two logarithms as a single logarithm. So these two will combine as log base b. And then the first argument, which is x to the 2/3, will be your numerator. And then the second argument, which is just y to the 5th, will be your denominator. Now bring down this next logarithm like that. All right, cool. Now, I see that I have a sum of two logarithms, a sum of two logs. Now, the product rule says you can rewrite a sum as of two logarithms as a single quantity. All you would have to do is multiply your arguments. The first argument is x to the 2/3 over y to the 5th, this times the second argument, which is x plus 4 quantity cubed. Technically, you're done. You rewrote this as a single logarithm, but please allow me just to clean this up just a little bit, all right? So then this is equal to log base b. Let's see. I'm going to rewrite this as x plus 4 quantity cubed times, I feel led to do this. Don't forget that x plus 4 quantity cubed really has an invisible denominator of 1. So just multiply straight across here in order to get what I'm writing. Now, you have x plus 4 quantity cubed, and then this one right here, folks, we learned in a few lessons ago that x to the power of 2/3 is the same thing as the cube root of x squared. All of this is over y to the 5th. So I just cleaned it up just a tad here. I changed rational exponents to radical notation here. And then I wrote x plus 4 quantity cubed just out front there. Because whenever you have a radical, you don't really want anything hanging out after the radical. So that's why I put x plus 4 quantity cubed first. All right, everybody. I hope you enjoyed learning about the properties of logarithms. Happy studying. I'll catch you in the next lesson.